Welcome, curious minds, to another deep dive. Today, we're plunging into a truly fascinating corner of organic chemistry, the world of organometallic compounds of group 1 and 2 metals. These might sound like complex laboratory reagents, but trust me, they are, well, foundational tools indispensable for building almost any complex molecule you can imagine. Think pharmaceuticals, advanced materials.
Absolutely. They're everywhere in synthesis.
So we're going to unpack their power, understand how they work, and reveal why they're such a big deal in modern synthesis.
Our mission today is really to give you a shortcut to being truly well-informed about these crucial regions. We'll explore not just what they are, but why they behave the way they do.
All right. The why is always key.
Exactly. And how their unique properties are harnessed in practical synthetic applications. We'll define all the necessary terms clearly, so whether you're reviewing for a meeting, maybe catching up on the field, or just driven by curiosity, you'll walk away with those satisfying aha moments.
Love those moments. Okay, so we're going to begin with the workhorses of this field, the Grignard reagents and organolithium compounds.
The classics.
The classics, yeah. Before journeying into the more specialized realms of zinc, cadmium, mercury, indium, and lanthanide organometallics.
A whole zoo of metals.
It really is. It's a story of chemical ingenuity that dates back over a century, yet remains incredibly relevant for the molecules we create today. So what do these compounds do, and why are they so powerful? Let's unpack this.
Okay, so at its heart, right, organometallic chemistry. It involves compounds where you've got a carbon atom bonded directly to a metal.
Carbon to metal, got it.
And that bond is inherently polar, meaning the electron density shifts significantly towards the carbon.
Ah, okay, so the carbon gets loaded up with electrons, becomes negative-ish?
Precisely, which transforms it into a highly reactive, electron-rich carbon nucleophile. It's poised to form new bonds in ways it couldn't otherwise.
So you're giving carbon a new superpower, essentially.
That's a great way to put it. It fundamentally changes the landscape of organic synthesis, allowing us to stitch together carbon chains with, well, remarkable precision.
That idea of giving carbon a superpower really helps visualize it. And the origin of this power, especially for group 1 and 2 metals, traces back to some truly groundbreaking discoveries, doesn't it? Right, our story, a true revolution in chemistry, begins around 1900 with Victor Grignard's groundbreaking discovery.
A Nobel Prize winner for this work, actually.
Wow. So he found that by reacting alkyl and aryl halides with magnesium metal in a solvent like diethyl ether, right?
Yeah, the ether solvent was crucial. And you form these incredibly useful organomagnesium compounds, famously known as Grignard reagents, typically represented as RMGX.
And incredibly useful sounds like an understatement.
Oh, it absolutely is. These Grignard reagents proved to be exceptionally reactive carbon nucleophiles. They were, and still are, a massive game changer for building new carbon-carbon bonds.
Which is like the holy grail of organic synthesis, right? Making CC bonds.
It's certainly a cornerstone. Before Grignards, forming these bonds with precision was often difficult, inefficient, just plain hard work. Their discovery truly opened up new synthetic pathways.
So once you have this powerful reagent, what can it do? What are its fundamental reactions?
Okay, so their primary synthetic value lies in their ability to react with polar multiple bonds, especially carbonyl groups. See double bond O, found in molecules like aldehydes and ketones.
Ah, the classic Grignard addition to carbonyls.
Exactly. That reaction lets chemists create a wide variety of alcohols.
Right.
But their utility extends further. They can react with other electron-deficient molecules, things like sil halides and nitriles leading to ketones.
Okay.
And if you react them with carbon dioxide dry ice, often you can form carboxylic acids.
Wow, versatile.
Very. To visualize it, imagine the R group from RMGX. That's the carbon nucleophile. It attacks the electron-deficient carbon of a carbonyl group. After some workup steps, usually adding acid,
You get an alcohol.
you get an alcohol. If that R-grid group attacks a nitrile, it'll ultimately yield a ketone after hydrolysis. This remarkable versatility makes them truly indispensable in a chemist's toolkit. Now, organolithium reagents, they came into synthetic use somewhat later than Grignards.
Okay.
But they quickly established themselves as equally important for synthesis due to their, well, unique reactivity profile. In fact, in many situations, they're actually the preferred choice.
And while both Grignards and organolithiums are powerful, is there a subtle difference in their reactivity? Are they interchangeable or?
Not entirely interchangeable. While both are incredibly useful, there's a subtle but significant difference in their reactivity and preferred applications. Generally, reactivity can vary across the periodic table, Linné, K, and MgX, Carex.
Right.
But it's really the lithium and magnesium reactions that are by far the most commonly used in organic synthesis. They kind of strike that sweet spot.
A balance between being reactive enough to be useful and, I guess, controllable enough to be practical?
Exactly that. You don't want something so reactive it just destroys everything.
Speaking of composition, Grignard reagents are often written simply as RMGX. What about organolithium compounds? Are they just simple RLI molecules floating around?
Good question. While we often write them as RLI for simplicity, organolithium compounds are more accurately represented as aggregates, like RLN.
Because they clump together.
Yeah, exactly. This N indicates their strong tendency to clump together into oligomers, dimers, tetramers, even hexamers, depending on the solvent in the specific organic group, the R group.
And that clumping must affect how they react, right?
Oh, profoundly. This aggregation profoundly influences their reactivity. The form they take in solution directly affects how accessible and reactive that carbon-lithium bond is to other molecules. It's a really critical aspect of their behavior you have to consider.
So if these compounds are so crucial, how do we make them in the lab? Let's start with Grignard reagents. What's the standard procedure, the go-to method?
A go-to method, is reacting magnesium metal, usually in the form of turnings or powder, with an alkyl or aryl halide and diethyl ether, or sometimes THF, tetrahydrofuran. It's a classic laboratory procedure. The reactivity of the halides follows a clear order, which is important for planning. Iodides react most readily, then bromides, and then chlorides. Chlorides are generally unreactive.
Ri, RBr, RCl. Got it. Can you give us some insight into how that bond between magnesium and carbon actually forms? What's the mechanism like?
Certainly. Well, the mechanism isn't perfectly understood in every detail, but the formation begins at the metal surface. It's believed to involve an electron transfer from the magnesium to the alkyl halide.
Okay, electron transfer.
Yeah, which leads to the formation and decomposition of a radical intermediate, specifically a radical anons, which then quickly fragments. This is followed by a rapid combination of the resulting organic radical with a magnesium species, maybe Mg plus or Mg atom, right at the surface, forming the RMGX bond.
Huh. So radicals are involved. There's often debate about how free these radicals are, right?
Exactly. There's been much discussion on whether the intermediate radical is truly free and diffuses away from the metal surface. There's some evidence, like small amounts of cyclized products from things like 5-hexanyl bromide, suggesting that cyclization does compete a bit with combination with the metal. That implied some diffusion.
So it might wander off a little before reacting.
A little, perhaps. You can even trap these alkyl radicals with specific scavengers. But the exact extent of radical diffusion remains, a point of academic debate. For aryl and vinyl halides, which form less stable radicals, an alternative mechanism through a dianion has even been suggested.
Fascinating. And what about stereochemistry? If we start with a chiral halide, say at a specific carbon center, do we retain that original 3D arrangement in the Grignard reagent?
Generally, no. When preparing Grignard reagents from typical alkyl halides, there's usually a loss of stereochemical integrity at the reaction site.
So it gets scrambled.
Pretty much. Stereoisomeric halides tend to yield organomagnesium compounds of identical composition. You lose the original stereochemical information. It gets racemized or epimerized.
But you mentioned exceptions earlier.
Yes, there are fascinating exceptions. Cyclopropyl and alkynyl systems, which have more constrained geometries, often react with partial retention of configuration. This is incredibly useful if you need to maintain a specific molecular architecture.
Okay, that's a key point for synthesis. And once the Grignard is formed, how stable is that stereochemistry? Does it invert easily?
Well, it depends. Once formed, secondary alkyl-magnesium compounds undergo stereochemical inversion only slowly. For example, some Norbornal systems take about a day at room temperature to reach equilibrium. NMR studies show inversion is quite slow even at high temperatures.
A day is pretty slow in chemical terms.
It is. But in stark contrast, the inversion of configuration for primary alkyl-magnesium halides is very fast.
Why the difference?
Good question. It might be due to a mechanism involving the exchange of alkyl groups between magnesium atoms, possibly via bridged intermediates. The larger steric bulk of secondary systems would simply hinder this process, effectively slowing down that molecular dance. And we also need to remember that the common designation RMGX is actually a simplification.
Right. You mentioned equilibria.
Exactly. In ether solutions, a dynamic equilibrium exists, known as the Schlenk equilibrium.
Yeah.
2 RMGX is in equilibrium with R2Mg plus MgX2.
Dialkyl magnesium and magnesium halide.
Correct. The position of this equilibrium depends on the solvent and the specific organic group. But for most simple Grignards in ether, the equilibrium lies well to the left, favoring RMGX.
Okay.
Importantly, solutions of organomagnesium compounds also exist as aggregated species. They clump together. Alkyl magnesium chlorides, for instance, are predominantly dimers in ether. Bromides and iodides show more complex behavior, maybe monomers in very dilute solutions.
And does the solvent change this clumping?
Oh yes. In tetrahydrofuran, PHF, there's less tendency to aggregate, and many Grignard reagents are found to be monomeric.
Monomeric meaning just single RMGX units.
Or perhaps R2Mg or MgX2 units, but not large clusters of RMGX together. And we can actually see these structures sometimes. X-ray crystallography has revealed them. Ethyl magnesium bromide, for example, exists as both a monomer with solvent coordinated and a dimer. It really shows how the solvent plays a crucial role in the precise structure and, by extension, the reactivity.
So these reagents aren't just simple molecules. They're dynamic clusters, constantly shifting. That's a profound effect of the solvent on their structure and reactivity. Okay, so we've explored the Grignards in detail. Now let's turn to their younger but equally powerful siblings, organolithium compounds. How are they crafted for synthetic precision?
Well, similar to Grignards, most simple organolithium reagents can be prepared by reacting an appropriate halide with lithium metal, usually lithium wire or dispersions.
Same principle, different metal.
Pretty much. This method is incredibly versatile for making alkyl, aryl, and alkanol lithium reagents. And again, like Grignards, simple alkylithium compounds generally lose stereochemical integrity during their preparation. It gets scrambled.
But I sense a but coming.
A key difference is that alkanolithium reagents, where the lithium is attached to a double-bonded carbon, typically retain the configuration of the double bond.
Ah, so cis stays cis, trans stays trans.
Largely, yes. Which is a vital feature for controlling the final shape of complex molecules, especially in stereoselected synthesis.
Are there ways to boost the efficiency of this preparation, maybe for trickier halides that don't react easily?
Yes, definitely. For some halides, using finely powdered lithium with a catalytic amount of an aromatic hydrocarbon is highly advantageous. Things like naphthalene or 4,4-DT-butylbiphenyl, often called DTBB.
Catalytic naphthalene, how does that work?
These conditions generate reactive radical anions, or dianions, like the naphthalene radical anion. These act as potent electron transfer agents, effectively converting the halide to its radical anion, which then goes on to form the lithium reagent.
Clever. So it sort of kickstarts the reaction.
Exactly. This technique is especially useful for preparing functionalized lithium reagents, allowing for more complex starting materials that might have sensitive groups which wouldn't survive harsher conditions. You can make things like lithiated acetyls this way.
That's really useful. Are there other non-halide routes to making organolithiums besides reacting with the metal?
Absolutely. Another valuable route involves the reduction of sulfides, using those same lithium radical anions like lithium nephthalenide or lithium DTBB.
Reducing sulfides, what kind of organolithiums does that give you?
This technique is particularly useful for synthesizing alithioethers, alithiosulfides, and alithiosolenes, where the lithium is on the carbon right next to an oxygen, sulfur, or silicon atom.
Okay, interesting class of compounds. And like Grignards, do organolithiums also clump together in solution? And how does that aggregation impact their utility?
They absolutely do clump together, maybe even more so than Grignards in some cases. Simple alkylithium reagents, for instance, exist mainly as hexamers in hydrocarbon solvents.
Hexamers, 6 units together.
Yep, 6 RLI units grouped together. In ethers, like THS, tetrameric structures usually dominate, often solvated with ether molecules coordinating to the lithium atoms. Phenolithium, for example, is a tetramer in cyclohexane, but a mixture of monomer and dimer in THF.
So again, the solvent is crucial.
Absolutely critical for understanding their form and function. And the degree of aggregation significantly impacts reactivity. Less aggregated species are generally more reactive.
Can you control the aggregation state? Maybe break up those clumps?
Yes, that's a key strategy. Chelating ligands, like tetramethylindinamide, are really important here. They coordinate strongly to the lithium centers and effectively reduce the degree of aggregation, often breaking tetramers or hexamers down into dimers or monomers.
making them more reactive.
Exactly. Even stronger donor molecules like HMPA, hexamethylphosphotriamide, or DMPU, and dimethylpropylurea lead to even more dissociated and therefore more reactive organolithium reagents. NMR studies confirm this. They show these ligands favor monomeric solvated species.
And can we actually see these aggregated structures?
We can. The crystal structures of many organolithium compounds have been determined. They provide direct evidence of these aggregated forms. Phenolithium, crystallized as an ether solvate, forms a tetrameric structure. It looks like lithium and carbon atoms at alternating corners of a highly distorted cube.
Distorted cube, wow.
Yeah, it's intricate. Each carbon is close to 3 lithiums, and an ether molecule coordinates to each lithium. It showcases this complex dance of atoms.
Okay, beyond reacting with halides or sulfides, there's another really crucial way to prepare organolithium reagents, right? And it seems to be all about precision, a method called lithiation.
That's right. Lithiation is a specific type of hydrogen-metal exchange, sometimes called metallation more broadly.
Hydrogen-metal exchange.
So you're swapping a hydrogen for a lithium.
Exactly. This is the standard approach for preparing alkyl-magnesium and alkylolithium reagents. It leverages the inherent acidity of the hydrogen bound to hybridized carbon, those triple bond carbons. They're acidic enough to be plucked off by a strong base, like an alkylithium.
Makes sense for alkenes, but it's not just for alkenes, is it?
Yes.
I've heard about directing groups playing a big role here. How did they work?
Ah, yes. For other types of organolithium compounds, lithiation is incredibly important. It's all about control and directing where that lithium goes. The position where lithiation occurs is determined by 2 main factors.
Okay.
First, the relative acidity of the available hydrogens. But second, and crucially, the directing effect of substituent groups already on the molecule.
So groups can sort of steer the lithium into place.
Precisely. Substituents that can coordinate to the lithium atom think groups with lone pairs like alkoxy or our amido NR2, sulfoxide SOR, sulfonol SO2R groups have a powerful influence on both the position and rate of lithiation, especially in aromatic compounds. How do they direct it?
They essentially guide the lithium to a specific orthosite, right next door to themselves on the ring. The lithium coordinates to the directing group first, and then the base part of the organolithium regent, like the butyl group in Buli, plucks off the adjacent proton.
Clever coordination effect.
Very. In heteroaromatic compounds like pyridine or furan, lithiation typically occurs adjacent to the heteroatom for similar reasons. Some groups, like certain protected amides or carboxyl groups, can even get deprotonated themselves. And the methoxy-mesoxy, MOM group, is particularly versatile because it directs lithiation well and can be easily removed later.
What makes a group a good director?
Well, these activating groups usually have an electron pair that can coordinate lithium and some polarity that helps stabilize the negative charge that develops on the carbon during proton removal. Geometry matters too. And surprisingly, even a small fluorine substituent, despite being electron withdrawing overall, is a very good directing group due to polar electrostatic effects.
Fluorine. Interesting. And what about the base use? Does it always have to be Buli?
Not always. Sometimes amide bases like LDA, lithium disopropylamide, or LTMP, lithium tetramethylpyridine, give better results than alkylithium reagents for lithiation, especially with tricky substrates. With these bases, fluorine has been shown to selectively promote ortholithiation, even winning out over traditionally strong directors like methoxy.
Sounds like there are ways to fine-tune the reaction conditions to make it even faster and more selective, too.
Oh, absolutely. Adding tertiary amines, especially timida, is a classic trick. It facilitates lithiation by coordinating at the lithium, breaking up those aggregates we talked about, and making the lithium regent more available to react.
So timida helps break the clumps and speeds things up.
Exactly. And kinetic and spectroscopic evidence suggests that, for example, lithiation of anisole, methoxybenzene, with Buli in the presence of timida involves a solvated dimeric species. Isotope effect studies confirm that proton abstraction is the rate-determining step.
So it's definitely pulling off the proton that's the slow part.
Yes. And it's likely there's a precomplexation step, where the anisole and the organometallic dimer get together before the actual proton transfer happens. Computational models have even visualized these transition states.
What do the models show?
They show the lithium, nearly in the aromatic plane, coordinated to the directing group, like the oxygen of the methoxy group or the fluorine. They reveal a significant electrostatic component stabilizing the transition state. They also suggest that coordinating the lithium actually decreases the directing group's ability to donate electrons via resonance, pytonation, but enhances its electron withdrawing inductive effect, a combination that activates the ortho position.
That's a really detailed picture. So is lithiation only for aromatic wings? Can it work on alkyl groups too?
Lithiation of alkyl groups is also possible, but again, it usually requires some help. A combination of donor chelation, a nearby group coordinating the lithium, and polar stabilization of the developing negative charge. Amides and carbamates, for example, can often be lithiated at the A carbon, the one right next to the carbonyl or nitrogen.
Okay. And you mentioned the Shapiro reaction earlier.
Yes, alkyl lithium compounds are crucial intermediates in the Shapiro reaction. It's a highly effective route to get vinyl lithium compounds starting from a ketone via a tosyl hydrazone intermediate.
Right. And what about just plain hydrocarbons? Can you lithiate those?
Generally, unactivated hydrocarbons are very reactive, but you can use really powerful superbase mixtures, like N-butyllithium mixed with potassium T-butoxide. That combination is strong enough to generate allyl anions from simple alkanes, like isobutene. Okay, moving on to another really vital method for preparing organolithium reagents, halogen metal exchange.
Halogen metal exchange. Swapping a halogen for a lithium?
Precisely. This is a very fast reaction, typically carried out at extremely low temperatures. We're talking negative 60 degrees C, negative 78 degrees C, sometimes even down to negative 120 degrees C.
Wow, that's cold. What drives this reaction and why is it so fast even when it's practically frozen?
The reaction proceeds thermodynamically in the direction that forms the more stable organolithium reagent. Essentially, the lithium ends up attached to the carbon that's part of the more acidic corresponding hydrocarbon.
So stability drives it, like lithiating the more acidic CH bond, but here it's swapping with a CX bond.
Exactly. So using highly basic organolithium compounds like N-butyl or T-butyllithium, you can readily exchange halogen substituents, especially bromine or iodine, at more acidic sp2 carbons like an aryl or vinyl halides to give the corresponding lithium compound.
And why the low temperature?
The low temperature requirement is a significant advantage. It allows you to perform the exchange quickly before the highly reactive organolithium reagent can react with other sensitive functional groups that might be present in the molecule. You can prepare arylithium compounds containing things like cyano or nitro groups this way, groups that would definitely react under the harsher conditions needed for preparation directly from lithium metal.
So it's fast, clean, and tolerates functional groups because it's done so cold.
That's the key benefit, yes. For alkyl halides, halogen metal exchange is a bit trickier due to competing side reactions like alkylation or elimination. But primary alkylithium reagents can still sometimes be prepared from iodides under carefully controlled low-temperature conditions.
And what about stereochemical insights here? If you start with a chiral halide or a specific vinyl halide isomer, do we retain configuration?
Well, for most typical alkyl systems, the degree of stereochemical retention during exchange is low. It gets scrambled again. BUT. It's normally very high for cyclopropyl and vinyl halides.
Okay, so geometry is preserved for those rings and double bonds.
Yes. And importantly, once formed, both cyclopropyl and vinyl lithium reagents retain their configuration quite well, even if warmed up towards room temperature. So you can make specific cis or trans alkylolithiums, for example, by starting with a corresponding cis or trans vinyl bromide and doing the exchange at low temperature.
That gives chemists really precise control over the shape of their molecules.
Absolutely. One practical note. Sometimes you need two equivalents of the alkylithium reagent, like T-butyllithium.
Why two?
Because the alkyl halide formed as a byproduct of the exchange, in this case, T-butyl bromide or iodide, can react with the first equivalent of the organolithium reagent you formed. So the second equivalent of bulite ensures the exchange goes to completion and maybe reacts with the byproduct. Another variation uses lithium naphthalenide for the exchange as well. All right, our third useful method for preparing organolithium reagents involves metal-metal exchange, often called transmetallation.
Transmetallation. Strategic swapping of metals between two different organometallic compounds.
Exactly that. You're swapping the organic groups between two different metals.
What's the core principle governing this exchange? What decides which metal gets which organic group?
The core principle is elegant and based on thermodynamics again. The reaction between two organometallic compounds will proceed in the direction that places the more electropositive metal bonded to the carbon atom that corresponds to the more acidic hydrocarbon.
More electropositive metal goes with the more stable carbanion, essentially.
You got it. It's driven by forming the most stable organometallic species overall. From a practical synthetic viewpoint, exchanges between organotin reagents, organostannins, and alkylithium reagents are particularly significant.
Tin lithium exchange, why is that so useful?
Because vinyl stand-ins are relatively easy to make, for instance, by adding tin hydrides across alkynes. Then, reacting the vinyl stand-in with something like N-butyllithium cleanly swaps the tin for lithium, giving you the valuable alkyl lithium compound.
Ah, so it's a reliable way to get those alkyl lithium.
Yes, and a key advantage of this transmetallation, particularly with things like alkoxy stand-ins, is that these exchange reactions often occur with retention of configuration at the carbon-metal bond.
Retention again, so you keep the 3D arrangement.
Exactly. This allows for precise control over the stereochemistry of the resulting organolithium compound, which is absolutely critical when you're building complex chiral molecules step by step.
Okay, now that we've got a really good handle on how to prepare these powerful organometallic workhorses, grignards, and organolithiums primarily, let's dive into their incredible versatility. What do they actually do in synthesis?
Right. These compounds are strongly basic and strongly nucleophilic. That combination makes them fantastic tools for building new carbon bonds and transforming functional groups, the real building blocks. Let's start with alkylation, using them to add alkyl groups to other molecules. While organomagnesium and organolithium compounds are superb nucleophiles, their direct use in simple SN2 substitution reactions, well, it's somewhat limited in practice.
Limited, but they're strong nucleophiles. Shouldn't SN2 work well?
You'd think so, but they're so reactive and also strong bases that other processes often compete. Electron transfer leading to radical reactions is a common problem, which can mess up yields or create unwanted byproducts. Elimination reactions where they act as a base instead of the nucleophile can also happen.
Ah, okay, so it's not always clean substitution. When does it work best?
The best results for simple SN2 type alkylation are typically achieved with reactive, unhindered electrophiles like methyl iodide or other primary iodides and sometimes bromides. Benzyl and allyl halides also work reasonably well.
Anything you can do to help the substitution win over the side reactions.
Sometimes adding HMPA, hexamethylphosphorotriamide, can help. It solvates the lithium ion strongly, breaks up aggregates, and seems to suppress some of the electron transfer pathways, accelerating the desired SN2 reaction and improving yields.
Does the type of organolithium reagent matter? Are some better at alkylation than others?
Absolutely. Organolithium reagents, where the carbanionic charge is delocalized through resonance, think allyllithium and benzolithium reagents are often much more effective in alkylation reactions than simple localized alkylithium reagents like Boole.
Why is that?
They're generally softer nucleophiles and perhaps less prone to side reactions. For instance, alkylation of these resonance-stabilized reagents with secondary alkyl bromides often proceeds with a high degree of inversion of configuration at the bromide center, allowing for good stereo control. Similarly, alkanolithium reagents can often be alkylated in good yields by alkyl iodides and bromides.
Can you alkylate lithiums?
It can be tricky, but their reactivity and alkylation can sometimes be significantly accelerated by including potassium alkoxides in the reaction mixture. This allows reactions like putting an ethyl group onto a fluoro-substituted aerolithium.
And you mentioned allylic halides work well as electrophiles.
Yes, alkylation by allylic halides is usually a satisfactory reaction. Interestingly, in this case, the reaction might even proceed through a cyclic, six-membered transition state.
A cyclic mechanism, does that affect where the bond forms?
It can. It can lead to allylic rearrangement. For example, if you react phenolithium with an allyl chloride that's labeled with carbon-14 at one end, a lot of the product ends up with a label at the other end of the allyl group, indicating a rearrangement occurred during the substitution.
Sneaky rearrangement. Beyond just extending chains, can these reactions be used to couple different types of molecules or even close rings?
Indeed. It's possible to couple certain lithiated reagents, like lithiated amides, with aryl and vinyl halides. These probably proceed by a very fast halogen-lithium exchange happening first, generating an alkyl halide in situ, which then undergoes substitution.
Okay, and ring closing.
Intramolecular reactions are incredibly useful for forming small rings, especially 3, 4, and 5-membered rings. Reacting 1,3, 1,3, 1,4, or 135 diodides with T-butyllithium is an effective way to make cyclopropane, cyclobutane, and cyclopentane derivatives in high yield.
But not bigger rings.
It's less effective for making larger rings. 136 diodides, for instance, give very little cyclized product, mostly just intermolecular reactions or reduction.
Good to know. And can you do these alkylations on really complex organolithiums, maybe ones with other functional groups or specific stereochemistry?
Yes, even complex functionalized organolithium reagents can often be prepared and alkylated while maintaining specific stereochemistry. There are examples where stereoisomers of lithiated cyclic ethers were methylated with retention of configuration.
What about making bonds to silicon or tin?
That works very well. Both trial-kill-subtle halides, like TMSCl, and trial-cool-stanyl halides generally give high yields of substitution products with organolithium reagents. It's a really important and reliable route to make organosulins and organostanins, which are themselves useful synthetic intermediates.
And how do Grignard reagents compare here? Are they better or worse for alkylation?
Grignard reagents are generally somewhat less reactive toward alkylation than their lithium counterparts. They're more prone to those electron transfer side reactions. However, they can still be synthetically valuable, especially when reactive electrophiles like methyl, allyl, or benzyl halides are involved. And useful alkylations of Grignard reagents can also be carried out with alkyl sulfonates like tosylates and sulfates, which can sometimes be better leaving groups than halides.
Okay, now let's turn to perhaps the most iconic and synthetically powerful application of these reagents, their reactions with carbonyl compounds. C double bond O. This is truly the heart of their utility, isn't it?
Absolutely. This is bread and butter stuff for organic synthesis. Indeed, the addition of Grignard reagents to carbonyl groups is arguably their single most important synthetic application. It's a cornerstone reaction taught in every introductory organic chemistry course for a reason.
The mechanism involves that cyclic transition state you mentioned.
Yeah, the transition state for Grignard additions is often depicted as a cyclic array involving the magnesium, the carbonyl oxygen, the carbonyl carbon, and the R group being transferred. Sometimes it might even involve two molecules of the Grignard reagent coordinating. There's good evidence supporting these kinds of aggregated multi-component transition states. It allows for a concerted delivery of the carbon nucleophile to the carbonyl carbon.
So depending on the starting carbonyl compound, aldehyde, ketone, ester, etc., we can craft different kinds of products, from alcohols to ketones.
Exactly. The outcome depends critically on the nature of the carbonyl compound. If you start with an aldehyde, except formaldehyde, you get a secondary alcohol after workup.
RCHO gives RCH.
Correct. If you start with a ketone, you get a tertiary alcohol. RCOR gives RCOR.
Okay. What about esters? They also have a carbonyl group.
Right. But when the carbonyl carbon has a potential leaving group, like the AOR group in an ester, the initial tetrahedral adduct formed after the first Grignard addition is unstable. It can collapse, kick out the alkoxy group, and regenerate a CO bond, forming a ketone intermediate in situ.
Ah, so the reaction doesn't stop there.
Usually not. This new ketone is typically more reactive towards the Grignard reagent than the original ester was, so it immediately undergoes a second addition step with another molecule of Grignard reagent.
Giving a tertiary alcohol again, but with two identical R groups from the Grignard.
Exactly. R-CAR ends up as RCOH after reacting with two equivalents of RMGX. This means you typically don't isolate ketones when reacting Grignards with esters. You go straight to the tertiary alcohol.
Okay, so esters give tertiary alcohols. What if you want a ketone?
There are several ways. Grignard reagents readily add to nitriles, RCA, after hydrolysis of the intermediate imine salt during workup. A ketone, RCOR, is obtained. Hydrocarbon solvents are often preferred for these reactions.
Nitriles to ketones.
Yeah.
Any other ways?
Yes, ketones can also be prepared from acyl chlorides, RCOCl. However, you have to be careful here to avoid the same problem as with esterization of a second Grignard to the ketone product.
How do you control that?
You typically run the reaction at very low temperatures, maybe negative 78 degrees C, and often use an excess of the acyl chloride, adding the Grignard slowly. THF is usually the solvent of choice here.
Low temp, excess acyl chloride. Makes sense. Are there even better ways?
There are some cleverer strategies. Using things like 2-pyridiethylate esters as the carbonyl source works well. Or a very popular method involves using N-methoxy and methylamides, often called wine-rebamides.
Wine-rebamides, how do they stop the second addition?
The initial tetrahedral adduct formed after the Grignard adds to a wine-rebamide is stabilized by chelation involving the magnesium ion, the oxygen, and the N-methoxy group. This stabilized adduct doesn't collapse to the ketone until you add aqueous acid during workup. So the ketone is only liberated after all the Grignard reagent is gone, preventing overaddition.
Very clever stabilization. What about aldehydes? Can we make those with Grignards? I thought adding to formaldehyde gave primary alcohols.
Adding to formaldehyde does give primary alcohols, yes, but you can make other aldehydes. One way is to react the Grignard reagent with triethyl orthoformate, HCOET3.
Orthoformate, like a protected formic acid?
Sort of. The addition step is actually preceded by the elimination of one of the alkoxy groups, generating an electrophilic oxonium ion, helped by the magnesium acting as a Lewis acid. The Grignard adds to this, forming a diethyl acetyl, RCHOET2.
And acetyls are stable to Grignards.
Yes, acetyls are stable under the reaction conditions, but hydrolyze easily to aldehydes, RCHO, with aqueous acid doing workup.
Okay. Any other routes to aldehydes?
Aldehydes can also be obtained by reacting Grignard reagents with certain formamides, like N-formyl piperidine. In this case, the initial adducts are stable, and the aldehyde is formed only upon hydrolysis.
It seems like Grignards can make almost anything.
They are incredibly versatile. Let's summarize the possibilities, like in Scheme 7.3 of the book. Primary alcohols. From formaldehyde, adds 1 carbon, or ethylene oxide adds 2 carbons. Secondary alcohols. From other aldehydes or from formate esters, like ethyl formate. Tertiary alcohols. From ketones or from esters, adding 2 R groups. Lactones give diols, aldehydes. From triethyl orthoformate or specific formamides, ketones. From nitriles, ethyl chlorides, carefully. Weinrebamides, or even some anhydrides, carboxylic acids. By reaction with CO2, carbonation, amines can be prepared from amines, aryan bonds, alkanes, often made indirectly by forming an alcohol and then dehydrating it.
That's a huge range of transformations from one type of reagent. It's no wonder they're so fundamental.
Absolutely. And Grignard reactions aren't just for the academic lab bench. They're used on an industrial scale, notably in drug synthesis.
Really? Can you give an example?
Sure. The syntheses of both tamoxifen and droloxifene, these are crucial estrogen antagonists used in breast cancer treatment, and for osteoporosis involve key Grignard addition reactions to build up their complex structures.
Wow. Life-saving medicines built with Grignards. Given their power, though, are there any challenges or functional groups that Grignard reagents just don't play well with?
Oh, yes. There are definitely limitations. Grignard reagents are quite sensitive to the types of functional groups present in the reaction partner.
Like what?
Well, acidic protons are a big no-no. Unprotected hydroxyl, amine N8, or thiol-S groups will just get deprotonated by the basic Grignard, consuming the reagent. Carbonyl groups in the same molecule will obviously react. And other reactive groups like nitriles, CN, and nitro-NO2 groups often cause problems or side reactions.
So you need to protect those groups first if they're present.
Often, yes. Or choose a different synthetic route. Things like alkene double bonds, ethers, and acetyls usually pose no problem, though.
What about steric hindrance if the molecules are really bulky?
That's another significant challenge. Grignard additions are sensitive to steric effects. With really hindered ketones, a competing process can become dominant. Reduction of the carbonyl group to an alcohol instead of addition.
Reduction? How does that happen?
The Grignard reagent transfers a beta hydrogen atom to the carbonyl carbon via a cyclic six-membered transition state, like the Meerwein-Pondorf-Verley reduction mechanism. The magnesium coordinates the oxygen, and a hydrogen from the Grignard's alkyl group gets delivered.
So instead of R adding, H adds.
Essentially, yes. The extent of this unwanted reduction increases with the steric bulk of both the ketone and the Grignard reagent. For example, reacting disopropyl ketone with isopropyl magnesium bromide gives almost entirely the reduction product, disopropyl carbonyl, with very little addition.
How can you minimize that?
Sometimes using nonpolar solvents like benzene or toluene instead of ether can help minimize this competing reduction.
Okay. Any other competing reactions?
Yes, another significant one is enolization of the ketone.
Enolization, pulling off an alpha proton.
Exactly. If the Grignard reagent acts as a base and deprotonates the I group of the ketone, it forms an unreactive magnesium enolate. The ketone is then simply recovered unchanged after you add acid during workup. The desired addition is completely shut down.
When is enolization most likely?
Enolization is particularly important when a considerable portion of the Grignard reagent might be present as magnesium alkoxide, which can form during preparation or storage due to reaction with oxygen or moisture. Like reduction, enolization becomes most competitive when the desired addition reaction is slowed down by steric factors.
So steric hindrance favors both reduction and enolization over addition. Tricky.
It can be. You have to choose your conditions and reagents carefully.
Now, I remember you mentioning earlier that some Grignards can undergo rearrangements. Is that true for simple saturated ones?
Generally, structural rearrangements are not encountered with simple saturated Grignard reagents. They're usually configurationally stable once formed, apart from the fast inversion of primary ones. However, allylic and homoallylic systems are different. They can undergo intriguing rearrangements leading to product isomerization.
Allylic ones again, what happens there?
NMR studies show that allyl magnesium bromide itself exists as a dynamic structure, maybe with some pi bonding character, and there's rapid equilibration between the two terminal carbons being bonded to magnesium.
So it's flipping back and forth.
Constantly. Similarly, substituted allylic Grignards, like 2-butynyl magnesium bromide and 1-methyl-2-propenyl magnesium bromide, exist as an equilibrium mixture in solution. And often, the addition products you get are derived from the minor rearranged isomer in that equilibrium.
Why would the minor isomer react faster?
It's believed to occur through a cyclic, six-membered transition state during the addition, which leads to an allylic shift, effectively delivering the less sterically hindered end of the allyl system, even if that's the minor species in solution.
Wow, complex dynamics. Does it happen with systems further away from the magnesium, like homoallylic?
It can. Even more complex. 3-butynyl magnesium bromide, where the double bond is one carbon further away, is in equilibrium with a small amount of cyclopropyl methyl magnesium bromide. We know this from deuterium labeling studies.
Ring chain tautomerism.
Essentially, yes. You can prepare cyclopropyl methyl magnesium bromide and its lithium counterpart at low temperatures, but at room temperature, the ring-opened 3-butynyl reagents are thermodynamically favored.
Interesting. What about even further out, like 5-hexanol? Does that cyclize?
That's a classic diagnostic tool. 5-hexanol magnesium bromide shows no such equilibrium with a cyclopentyl-methyl species. However, interestingly, the corresponding 5-hexanol lithium reagent does cyclize upon warming from -78 degrees C, forming cyclopentyl-methyl lithium. So lithium is different there.
Fascinating differences. And what about alkynes? Can they cyclize?
Yes, certain alkynyl lithium reagents, and alkanol, can undergo exocyclization reactions to form cycloalkyldene isomers rings with an exocyclic double bond where the lithium used to be.
What drives those cyclizations?
The driving forces are usually the formation of an additional carbon-carbon bond and the generation of a more stable carbanion, sp2 hybridized versus b3.
That's quite a molecular dance happening with these reagents. Is there a way to avoid preparing the organometallic reagent separately, maybe if it's unstable or prone to these rearrangements?
Yes, there's a technique called the Barbier reaction.
The Barbier reaction.
Yeah, it involves generating the organometallic intermediate in situ, meaning right there in the reaction flask in the presence of the carbonyl compound or other electrophile. It reacts immediately as it's formed.
So you mix the halide, the metal, and the carbonyl compound all together.
Essentially, yes. While it often offers no advantage for stable Grignard or lithium reagents that you can easily preform, it's very useful when the organometallic reagent itself is highly unstable or difficult to prepare and isolate.
It's like those allylic halides.
Exactly. Allyl halides can be difficult to convert to Grignard reagents in good yield due to coupling side reactions. They frequently give better results for carbonyl additions using the Barbier procedure. Because you're using solid metals, like magnesium or lithium, the physical state of the metal affects the reaction rate.
Can you speed it up?
People have found that using ultrasonic irradiation can favorably impact the Barbier reaction, presumably by activating the metal surface and accelerating the generation of reactive organometallic species.
Okay, we've covered Grignards and their carbonyl reactions extensively, including the pitfalls. How do organolithium reagents compare? Are they better, worse, just different?
Well, the overall reactivity of organolithium reagents toward carbonyl compounds is generally similar to that of Grignard reagents. They do the same kinds of additions.
But are there advantages?
Yes, significant advantage is that lithium reagents are generally less likely to undergo that competing reduction reaction with ketones, especially hindered ones.
Less reduction, that's huge.
It is. This makes them the preferred choice for synthesizing highly substituted alcohols where steric hindrance might cause problems with Grignards. For example, adding ethyl lithium to adamantone, a very bulky ketone, gives almost entirely the desired tertiary alcohol, 97% yield, whereas ethyl magnesium bromide gives mainly the reduction product.
So, for tricky additions, lithium is often better than magnesium. What about controlling regio selectivity with our-day unsaturated ketones? Those compounds with a CC next to the CO have two places to react. The carbonyl carbon, 1-value-2 addition, or the beta carbon of the double bond, 1-value-4 or conjugate addition.
That's a great point, and a classic challenge in synthesis. Organolithium compounds can add either way.
Which way do they prefer?
Highly reactive, simple organolithium reagents like BuLi usually react by 1-value-2 addition, attacking the carbonyl carbon directly. If you want one vital 4 addition, chemists often use organocopper reagents, like Gilman reagents, artraceli, which are much better at it.
Okay, copper for 144, but can you get 1-PLA4 addition with just lithium reagents?
Sometimes, yes, even without copper. It's been found that adding small amounts of HMPA to the reaction mixture can actually favor 1-PLA4 addition with some organolithiums.
HMPA again. How does it switch the selectivity?
The thinking is that HMPA strongly solvates the lithium ion, reducing its Lewis acidity. This makes the lithium less likely to coordinate strongly to the carbonyl oxygen, which is thought to direct the 1 of and 2 attack. By attenuating that coordination, HMPA subtly changes the reaction pathway, allowing the conjugate 1-mel4 addition pathway to compete more effectively.
Very subtle control mechanism. Now, I recall you mentioned that making ketones directly from carboxylic acids is notoriously bad with Grignards. Is that another area where organolithiums shine?
Precisely. That reaction RCOH plus 2 RIU RCOR is actually quite efficient for lithium reagents, whereas it's usually terrible for Grignard reagents.
Why do lithium reagents work so much better here?
The success relies on the stability of the intermediate that's formed. When the first equivalent of RLI deprotonates the acid, RCOH RCOLI, the second equivalent adds to the carbonyl group. This forms a stable dilithioadduct, sort of like RCOI2R.
A dilithiohemiacetal analog.
Something like that. The key is that this intermediate is stable under the reaction conditions. It doesn't break down to release the ketone until you add aqueous acid during workup.
Just like the wine-rebamide intermediate.
Exactly the same principle. It prevents the ketone, RCOR, from being formed while there's still reactive RLI present, thus avoiding the overaddition to form a tertiary alcohol, RCOHR2.
That's a really useful reaction then. Any practical tips for running it?
A common challenge is still preventing that tertiary alcohol formation if any excess lithium region is present when the ketone is liberated during hydrolysis. One strategy is to use exactly 2 equivalents of the organolithium region, making sure it's all consumed before workup.
Tricky to get the stoichiometry perfect.
It can be. Alternatively, a clever trick is to quench the reaction mixture not with acid, but with trimethylsilate chloride, TMSCl first. This traps the intermediate as a stable bisilate acetal, R-cosmin-32, RFR. Then you hydrolyze this stable species gently with dilute acid to get the ketone without any RLI around to cause trouble.
Nice workaround. Can you do sequential additions?
Yes, this approach can even be extended to a tandem one-pot process for synthesizing unsymmetrical ketones. You add 1 alkylithium, or Li, to the carboxylate, maybe trap the intermediate, then add a different alkylithium, RLi, before the final hydrolysis.
Wow, that's powerful. And what about those wine-rebamides? Do they work with organolithiums too?
Yes, N-methyl N-methoxyamides, wine-rebamides, are also valuable starting materials for preparing ketones with organolithium reagents, just like with Grignards. Again, the success depends upon the stability of that chelated tetrahedral intermediate, preventing elimination and a second addition step until workup.
So summing up for organolithiums, what's their broader range of applications beyond just alcohols and ketones from carbonyls?
Okay, let's look at the bigger picture, like Scheme 7.4. Organolithium reagents perform a wide variety of crucial transformations. Alkylation. Beyond simple SN2, they are excellent for things like epoxide ring opening, demonstrating their strong nucleophilicity. Alcohol formation. Crucially, used for forming alcohols by additions to aldehydes and ketones, often with better control over side reactions than Grignards. Ketone formation. They can produce ketones cleanly from carboxylate salts, acylchlorides, acid anhydrides, and especially wine-rebamides. Carboxylic acids. Easily formed by carbonation, reacting with CO2. Aldehydes, synthesized by reactions with DMF, dimethylformamide. The intermediate adduct hydrolyzes to the aldehyde. Stabilize the allylic alkylation. They're also capable of alkylating stabilized allylic lithium reagents effectively.
So a very broad toolkit.
Extremely broad. And it's really important to recognize that in addition to all these applications as nucleophiles, organolithium reagents, especially the commercially available ones like methyl, N-butyl, sec-butyl, and tert-butyllithium, hold enormous importance in synthesis, simply as incredibly powerful bases for deprotonation. And as lithiating reagents for that hydrogen-metal exchange we discussed earlier, they drive countless other transformations in organic chemistry.
Okay, we've seen the power, the scope, the pitfalls. Now let's talk about the finesse of these reactions, controlling the three-dimensional shape of the molecules we build. Stereoselectivity. How do Grignards and organolithiums behave when they add to chiral molecules or molecules that can form chiral products?
Right. When organomagnesium and organolithium compounds add to simple cyclic ketones, like substituted cyclohexanones, their stereochemistry is actually quite similar.
How so?
With unhindered cyclohexanones, The stereoselectivity isn't always extremely high, but there's generally a preference for the nucleophile to attack from the equatorial direction.
Equatorial attack, meaning the R group comes in from the side rather than from the top or bottom.
Exactly, which leads to the formation of the alcohol where the new OH group is pointing axially. This preference for the equatorial approach generally increases as the size of the alkyl group, the R group, on the organometallic region gets bigger.
More steric hindrance pushing it to attack from the side.
That's the simple picture, yes. For alkylithium reagents, adding certain salts like lithium perchlorate, LiClO4, can sometimes significantly improve the stereoselectivity, enhancing the proportion of the axial alcohol product for reasons that are still debated.
What about more complex ring systems like bicyclic ketones?
For more rigid structures like bicyclic ketones, for example, norbornenone, the stereochemistry is usually dominated by sterics. The organometallic region simply adds from the less hindered face of the carbonyl group. That's often quite predictable.
Okay, predictable steric control. What about adding to carbonyl compounds that are already chiral, maybe with a stereocenter nearby?
The stereochemistry of addition of organometallic reagents to chiral aldehydes and ketones often mirrors the behavior we see with hydride-reducing agents, like lithium aluminum hydride. The outcome can often be predicted using models like Cram's rule or the Filkin-Ann model.
Cram's rule involves minimizing steric interactions in the transition state.
Essentially, yes. The interpretation of this stereoselectivity can be made in terms of a complex interplay of steric effects, bulkiness, torsional strain, eclipsing interactions, and stereoelectronic effects, orbital alignments, within the transition state. It gets quite sophisticated.
Does complexing the metal ion affect the stereochemistry?
Interestingly, yes. Adding crown ethers, which are known to complex metal ions like Mg2+ or Li+, can sometimes enhance stereoselectivity in both Grignard and alkylithium reactions.
Why would trapping the metal ion help?
The effect is often attributed to a decreased electrophilicity, or Lewis acidity, of the metal cation when it's complexed by the crown ether. This leads to attenuated reactivity. The reaction slows down a bit, and this often allows the more subtle factors controlling stereoselectivity to have a greater influence, leading to a higher preference for one product isomer.
Slower reaction, more selective outcome. Makes sense. What if there's a group nearby that can grab onto the metal, like chelation control?
Yes. Chelation control is a very powerful concept here. For ketones and aldehydes, where an adjacent substituent, like an alkoxy group, amino group, etc., has lone pairs that allow for chelation with the metal ion Li+ or Mg2+, the stereochemistry can often be elegantly explained and predicted by considering the steric requirements of the resulting rigid, chelated transition state.
So the molecule kind of folds around the metal ion.
Exactly. In alkoxy ketones, for instance, it's assumed that both the alkoxy oxygen and the carbonyl oxygen coordinate to the metal ion in a 5-membered ring. Addition to the R group then occurs preferentially from the less sterically hindered face of this rigid chelate structure.
And does this accurately predict the outcome?
Very often, yes. It correctly predicts the major stereoisomer formed, sometimes with ratios dominating by as much as 100.1 for certain Grignard reagents. Further supporting the importance of chelation is the observation that these chelating groups not only increase stereoselectivity, but often also accelerate the reaction rate compared to non-chelating analogs.
Faster and more selective, that's counterintuitive to the crown ether example.
It seems so, but it makes sense here. The chelation not only favors a specific transition state geometry, leading to selectivity, but also lowers the overall activation energy barrier by providing optimal metal ion complexation and activation of the carbonyl group, leading to rate acceleration.
Very elegant. Now, the ultimate goal, enantioselective additions. Creating just one mirror image when adding to a non-chiral ketone, for example. Can we do that with Grignards or organolithiums?
Generating a new stereogenic center enantioselectively, preferentially forming one enantiomer over the other, when a Grignard or alkylithium adds to an unsymmetrical ketone is a significant challenge. Because these reactions are often very fast, achieving high enantioselectivity, high E, or enantiomeric excess, has traditionally been very difficult.
Too fast to control easily.
Often, yes. But exciting progress has been made, particularly using chiral ligands or additives. For instance, using the magnesium salt of tadol, that's a specific chiral dioligand, has been shown to promote highly enantioselective additions of Grignard reagents to certain ketones, like acetophenone.
Tadol, how does it work?
These specific reactions often occur under heterogeneous conditions, meaning not everything is dissolved, and are quite slow, especially at very low temperatures like -100 degrees Celsius. This suggests that the chiral tadidol ligand modifies the magnesium reagent, establishing a precise chiral environment around the reactive center that dictates the facial selectivity of the addition to the ketone. It's an elegant example of asymmetric catalysis, guiding the reaction to form predominantly one enantiomer. It shows how chemists can really influence molecular architecture at a very fundamental level. Okay, so while lithium and magnesium regions are clearly the cornerstones, the workhorses of group 1 and 2, organometallic chemistry, we shouldn't forget the others. The organometallic compounds of group IIb, that's zinc, cadmium, and mercury, and also group IIb, particularly indium, offer some really distinct advantages.
Different properties, different uses.
Exactly. These often stem from their more attenuated reactivity. They're generally less aggressive than Li or Mg reagents, and sometimes unique catalytic properties, which allows for finer control and synthesis.
What makes these group IIb and IIb metals different electronically from lithium and magnesium? What's their unique character?
Well, a key feature lies in their electronic configuration and stability. These metals, zinc, cadmium, mercury, and indium, have a filled D10 electronic configuration in their common oxidation states. +2 for group IIb, +3 for group IIb like indium.
A full D shell. That's usually stable.
Very stable. This filled D shell makes these oxidation states quite resistant to change. So reactions involving their organometallic derivatives typically do not involve changes in the metal's oxidation level during the main reaction steps. This is a key difference from many transition metals used in catalysis, which often cycle through different oxidation states.
Okay, stable oxidation state. How does that affect the C-metal bond?
Because these metals are less electropositive than the group Ia, like Li, and IIa, like Mg metals, the carbon-metal bonds in their organometallic compounds have significantly more covalent character. The bond isn't as polar, the carbon isn't as negatively charged.
Less polar bond, so less nucleophilic.
Generally, yes. Consequently, the nucleophilicity of their organometallics is usually less than that of corresponding organolithium or organomagnesium compounds. And this attenuated reactivity, as you called it, is precisely what makes them valuable in many cases.
Less reactive is good.
It can be. Many of their important synthetic applications rely on using a specific catalyst, maybe a Lewis acid or a chiral ligand, to promote the desired reaction. This combination of a less inherently reactive organometallic and a specific activator allows for much greater control and selectivity than you might get with the more indiscriminately reactive Grignards or organolithiums. They're more like precision tools rather than the powerful but sometimes clumsy sledgehammers of Li and Mvo.
That makes perfect sense. Precision tools. So let's start with organozinc compounds, which seem to be particularly versatile and widely used. How are they typically prepared?
There are several common ways. Organozinc reagents, R2ZN or RZNX, are often prepared simply by reacting the more common organometallics like Grignard or organolithium reagents with zinc salts, typically zinc chloride ZnCl2.
So transmetallation from Mg or Li to Zn.
Exactly. For example, treating a Grignard reagent with ZnCl2, often in the presence of dioxane, precipitates out the magnesium halides, leaving a solution of the alkyl zinc reagent. There's even a convenient one-pot method where you sonicate, use ultrasound on, an organic halide with magnesium metal and zinc chloride altogether.
Making the Grignard and immediately transmetallating to zinc. Clever. Can you make them directly from halides and zinc metal?
Yes, that's another route. Organozinc compounds can also be prepared directly from organic halides using highly reactive zinc metal, often prepared by reducing zinc salts with something like potassium metal, Reek zinc, or by using a zinc-copper couple. Simple alkyl zinc compounds like dimethyl zinc or diethyl zinc are actually distillable liquids and can be made this way. Several are commercially available.
What about aryl or allylic zinc reagents?
Aryl zinc reagents can be synthesized from aryl halides with activated zinc, or again via transmetallation from Grignards or aryllithiums. Allylic zinc reagents are particularly interesting. They can often be prepared in situ, meaning generated right in the reaction pot as they are needed even in aqueous solution in the presence of aldehydes for Barbier-type reactions.
Halyl zinc in water. That's surprising.
It is. And these allylic zinc reactions often show a strong preference for forming the more branched alcohol product, suggesting a cyclic Zimmermann-Traxler-type transition state similar to what we discussed for allylic Grignard reagents. Kinetic isotope studies support this cyclic mechanism.
Now, one of the biggest challenges we noted with Grignards and organolithiums was their sensitivity to other functional groups. Do organozinc reagents offer an advantage here? Can they tolerate more functionality?
Yes, and this is a major advantage. A particularly attractive feature of organozinc reagents is their significantly better compatibility with many functional groups that would interfere with, or be destroyed by, organomagnesium or organolithium reagents. Things like esters, amides, even sometimes ketones or nitriles can survive in the presence of many organozinc reagents.
So you don't need as many protecting groups.
Often, no. This allows for the synthesis of much more complex functionalized target molecules in fewer steps, opening up a broader range of synthetic possibilities that simply aren't feasible with the more reactive group ion 2 counterparts.
How do you make these functionalized organozinc reagents?
One way is via halogen metal exchange reactions,
Yeah.
this time using diethyl zinc, Et2-zinene, as the exchange partner with the functionalized alkyl or aryl iodide or bromide, Rx.
Diethyl zinc swaps with Rx. What drives that?
The equilibrium for this exchange can be driven to completion by using an excess of diethyl zinc and, importantly, by removing the volatile ethyl iodide or ethyl bromide byproduct through distillation. This allows the pure, functionalized organozinc reagent, R2-NN or RZNX, to be obtained after removing the excess diethyl zinc. These exchange reactions are often catalyzed by small amounts of transition metal salts, like manganese bromide, copper chloride, or nickel acetylacetoate NiCaC2, which allow them to proceed satisfactorily even with less reactive alkyl bromides.
Catalysis helping the exchange. Can you get them from other sources, maybe with stereochemistry?
Yes, another powerful route is preparing organozinc reagents from trialkylberenes through exchange with dimethyl zinc or disopropyl zinc.
Boron to zinc exchange. Why is that useful?
This route is especially powerful because it can be used to prepare enantiomerically enriched organozinc reagents. You start by performing an asymmetric hydroboration of an alkene, which is a well-established, highly stereoselective reaction, creating a chiral trialkylberene. Then you exchange one of the chiral alkyl groups onto zinc using something like disopropyl zinc.
So you transfer the chirality from boron to zinc.
Exactly. And importantly, the exchange reaction usually occurs with retention of configuration at the chiral center. So you can generate highly enantiomerically pure organozinc reagents this way, for example, starting from trisubstituted cycloalkenes. These chiral zinc reagents are then valuable for asymmetric synthesis. Alkynyl zinc reagents can also be made stereoselectively from alkenes using a hydrozincation reaction catalyzed by titanosyne dichloride, CP2CCl2.
Okay, so we have several ways to make organozinc reagents, including functionalized and chiral ones. Once prepared, how do they react, especially with carbonyls? You mentioned their attenuated reactivity means they often need a catalyst.
That's generally right. While pure organozinc compounds, like R2-ZN, are relatively unreactive toward direct addition to simple aldehydes and ketones, their reactions are very effectively catalyzed by both Lewis acids and coordinating ligands.
So they need a push.
They usually need a push. Interestingly, when organozinc reagents are prepared in situ from ZnZl2 and Grignard reagents, as in the first method we discussed, they do add to carbonyl compounds to give alcohols. This likely reflects activation of the carbonyl group by the magnesium salts, like MgCl2 or NgBr2, that are also present in the mixture.
Ah, the leftover magnesium acts as the Lewis acid catalyst.
Probably. In contrast, pure dialkyl zinc reagents often react poorly with ketones, sometimes favoring reduction over addition unless you add an activator. The addition of alkyl zinc reagents can also be effectively promoted by adding trimethylsilly chloride, TMSCl. In this case, you isolate the silly ether of the alcohol product.
Okay, so catalysis is key. This is where those highly enantioselective reactions come in, isn't it? Adding chiral ligands to control the stereochemistry of the addition.
Precisely. This has been one of the most impactful developments in organozinc chemistry over the last few decades, achieving remarkably high degrees of enantioselectivity, often 90% or even 99% E, when dialkyl zinc reagents, like diethyl zinc Et2-ZN, react with aldehydes in the presence of small amounts of chiral ligands.
What kinds of chiral ligands work?
Several classes of compounds have been successfully employed. Famous examples include chiral amino alcohols derived from ephedrine or norephedrine, viamino alcohols like exodomyleno, isoborneol, DAIB, chiral diols like tadel, chiral diamines, and phosphoramidites. These ligands coordinate to the zinc and create a chiral environment.
And how does this lead to such high selectivity? What's the mechanism thought to be?
The high enantioselectivity is a result of the chiral ligand chelating effectively to the zinc. The proposed transition state for the addition is believed to be quite complex, likely involving 2 zinc atoms in a catalytic cycle.
2 zinc atoms?
Yes. It's thought that 1 zinc atom, coordinated to the chiral ligand, acts as a chiral Lewis acid by coordinating to the carbonyl oxygen of the aldehyde, activating it. The other zinc atom, from the bulk Et2-ZN, serves as the source of the nucleophilic ethyl group that forms the new CC bond. The catalytic cycle probably involves various dinuclear zinc complexes formed among the zinc ligand chelate, the aldehyde, and the diol zinc reagent.
A complex dance involving multiple zincs and the ligand.
Exactly. Computational studies have explored the structures of these possible transition states, identifying different stereochemical arrangements. For the popular amino alcohol ligands, certain arrangements are preferred based on minimizing steric clashes. Ultimately, the specific structure and substituents on the chiral ligand precisely determine the facial selectivity of the addition to the aldehyde, dictating which enantiomer of the resulting secondary alcohol is formed preferentially, often with incredibly high fidelity.
That's incredibly elegant control. Does the type of R group on the zinc matter? Are aryl zincs different from alkyl zincs?
Interestingly, yes. Aryl zinc reagents are considerably more reactive than alkyl zinc reagents in these catalyzed additions to aldehydes. Computational models indicate that transferring a phenyl group to the carbonyl has about a 10 kilocomole lower activation energy than transferring an ethyl group.
Why the difference?
It's attributed partly to participation of the phenyl ring's pi system in the transition state, and also the greater electronegativity of the phenyl group compared to ethyl. This enhances the Lewis acidity of the catalytic zinc atom bonded to the phenyl group, facilitating the bond-forming step.
And do these precise reactions have implications beyond the lab bench? Can you scale them up?
Oh, absolutely. The practicality of these enantioselective zinc additions extends to industrial scale. Aspects of the scale-up using catalysts like N,N-diethylnorphydrine have been well studied, allowing for the production of important chiral alcohol building blocks with high enantiomeric excess. It's vital for producing specific enantiomers of drug molecules or fine chemicals efficiently.
Okay, so chiral ligands are one way to catalyze. What about simple Lewis acids?
Yes. Non-chiral Lewis acids also work well to catalyze additions, particularly titanium compounds like titanium tetrasopropoxide, TiO-IPR4, and also trimethylsilyl chloride, TMSCl, as mentioned before. For instance, reactions of iodozinc esters, Reformatsky-type reagents, with aldehydes are effectively catalyzed by titanium species, often giving excellent yields, sometimes leading directly to lactone products through subsequent intramolecular cyclization.
Can you get enantioselectivity with Lewis acids too?
Yes, if you use a chiral Lewis acid. For example, using chiral titanium tadol complexes as catalysts can induce high enantioselectivity, 95 to 99% E, in the addition of diol zinc to a variety of aldehydes. Another effective catalyst system involves using bis-trifluoromethensulfonamides derived from chiral diamines like trans-cyclohexene 1-GAC2-diamine, which also yield products with high E.
What about adding to ketones? They're usually less reactive.
They are. Ketones are inherently less reactive than aldehydes toward organozinc reagents, and achieving high enantioselectivity is generally much harder because the catalyst needs to differentiate between two carbon substituents on the ketone rather than a carbon substituent and a hydrogen. It's a tougher challenge.
But has there been progress?
Yes, some recent advancements have shown success. For example, using a specific chiral diol ligand derived from both trans-cyclohexane-amine and camphor sulfonic acid in conjunction with titanium tetrasopropoxide has achieved good yields and high enantiomeric excess, up to 99% E, for the addition of diethyl zinc to various ketones. The active catalyst is probably a dinuclear titanium species where the chiral ligand replaces some isopropoxide groups.
So progress on ketones too. Are there other carbonyl derivatives or related compounds that organozinc reagents react with?
Yes. Lewis acids also catalyze the reaction of alkyl zinc reagents with acyl chlorides, producing ketones efficiently and cleanly. And organozinc halides can add to reactive ammonium salts without needing an external catalyst, as these electrophiles are sufficiently activated. Often dilylamines are used in these reactions because the allyl groups can be easily removed later.
And the Reformatsky reaction, that's a classic zinc reaction, isn't it?
It absolutely is a classical named reaction where you react metallic zinc and a haloester, like ethyl bromoacetate, and a carbonyl compound, aldehyde or ketone, all together.
What's the product?
You get a V-hydroxyester after workup. The reaction proceeds through the formation of an organozinc intermediate, which is essentially the zinc enolate of the dehalogenated ester. This zinc enolate then acts as the nucleophile, attacking the carbonyl group.
A zinc enolate, so it's related to aldol chemistry too.
Exactly. The Reformatsky reaction is mechanistically related to both organometallic reactions, forming the organozinc, and aldol additions, the enolate adding to the carbonyl. It probably involves a cyclic transition state, similar to Grignard additions. Interestingly, the Reformatsky reagent derived from T-butyl bromoyl acetate has been crystallized and shown to be a dimer with both oxygen zinc enolate-like and carbon zinc, organometallic-like bonds, though the reaction likely occurs through the monomer.
Any ways to make the Reformatsky reaction work better?
Yes, various techniques can activate the zinc metal and improve yields. Pre-treating zinc dust with copper salts to form a more reactive zinc-copper couple is common. Exposing the zinc to TMSCl can also help. Even Wilkinson's catalyst, RHCl PPH33, has been shown to catalyze the formation of Reformatsky regions from diethyl zinc under very mild conditions. These mild conditions are also good for intramolecular versions of the reaction, forming cyclic U-hydroxy esters, often with good stereoselectivity. Zinc anylates prepared from high haloctones can also be used as nucleophiles in mixed aldol condensations.
Okay, that's a lot on zinc. Are there any other related organozinc reactions worth mentioning, expanding the toolkit?
Yes, a couple more things. Organozinc regions can be converted into more reactive anionic zincate species by mixing them with organolithium compounds.
Zincates,
Yeah.
like R3-zetum or R2-ZN-Xe.
Exactly. These anionic species are more nucleophilic than the neutral organozinc reagents and react directly with aldehydes and ketones to give addition products without needing other catalysts. The stoichiometry matters. You can form 1.1, 2.1, or even 3.1 lithium to zinc species.
Do zincates add to other things?
Yes, zincate regions can also add to imines, sometimes needing Lewis acid catalysis like BF3 for simple alkylamines, but often reacting directly with more activated imines. If the imines are derived from chiral amines, you can get diastereoselective addition.
Okay. Any tandem reactions involving zinc?
Yes, there's a clever one.
Sure.
Organozinc regions have been used in conjunction with abromidalboranes in a tandem sequence to synthesize Z-trisubstituted allylic alcohols stereoselectively.
How does that work?
After the vinyl borane is prepared, reaction with diethyl zinc causes a migration of one of the boron substituents to the adjacent carbon with inversion of configuration and an exchange of zinc for boron. Then adding an aldehyde traps the resulting allylic zinc species, yielding the Z-allylic alcohol after workup. It's a neat multi-step sequence.
Very intricate. One last zinc reagent.
The Lombardo's reagent. This is a fascinating reagent generated from zinc metal, dibromomethane, CH2Br2, and titanium tetrachloride, HCl4.
It converts ketones directly to methylene groups, COEC-2. It's a methylating agent, similar in outcome to the Wittig reaction, but mechanistically different.
How's it thought to work? The active reagent is presumed to be some kind of titanium-zinc dimethylated species, perhaps involving a TiCH2 or TiCH2ZN structure. This adds to the ketone, likely influenced by the Lewis acidity of titanium. Subsequent elimination involving the oxygen and titanium zinc then generates the methylene group. A similar procedure starting with esters and 1101 dibromocanes can give enol ethers. Okay, moving on briefly to organocadmium compounds. Cadmium is right below zinc in the periodic table.
How are they made?
Similar to zinc. They can be prepared from Grignard reagents or organolithium compounds by reacting them with cadmium salts, like CdCl2. They can also be synthesized directly from alkyl, benzyl, or aryl hydes by reaction with highly reactive cadmium metal, generated by reducing CdCls.
And how does their reactivity compare to organozinc compounds? Are they similar?
Yes, their reactivity is generally quite similar to that of the corresponding organozinc compounds that are also relatively unreactive unless activated.
What was their main use historically?
The most common historical application of organocadmium compounds, particularly dialkyl cadmiums, R2CD, was in the preparation of ketones by reaction with acyl chlorides. They were considered quite good for this, as they usually stopped cleanly at the ketone stage without adding a second time, even without the careful control needed for Grignards.
So why the declining role? Why don't we hear about them much now?
The major disadvantage, and the primary reason for their declining use in recent years, is the high toxicity and significant environmental problems associated with the use and disposal of cadmium and its compounds.
Ah, the toxicity issue.
Exactly. Cadmium is a heavy metal with serious health and environmental concerns. So while the chemistry is similar to zinc, the safety and environmental drawbacks have largely pushed organocadmium reagents out of mainstream synthetic use. Chemists prefer to use zinc or other less toxic alternatives if possible. All right, next in group IB is mercury, organomercury compounds.
Mercury, another heavy metal. How are these made?
Organomercury compounds can be prepared through several useful methods. The general metal exchange reaction between mercury salts like HgCl2 or HgREC2 and organolithium or Grignard compounds is applicable.
Okay, transmetallation again. Any other important routes?
Yes, the oxymercuration reaction is a very important and convenient way to synthesize certain functionalized organomercury reagents directly from alkanes. You react an alkane with a mercury salt in the presence of a nucleophile, like water or an alcohol.
Right. Oxymercuration demercuration is a classic way to hydrate alkanes, so you can stop after the oxymercuration step to get the organomercury compound.
Exactly. Organomercury compounds can also be obtained by reacting mercuric salts with trialkylboranes, though typically only primary alkyl groups transfer readily from boron to mercury. Alkynyl mercury compounds can be prepared via hydroboration of an alkane, followed by reaction with mercuric acetate. These compounds can often be used immediately in situ or sometimes isolated as organomercuric halides, RHGX.
So how do they behave as nucleophiles? Are they strong like lithium or magnesium, or more like zinc?
They are generally very weak nucleophiles, much weaker than zinc even. They really only react with very reactive electrophiles. For instance, they readily undergo electrophilic substitution by halogens like Br2 or I2, which cleaves the CH-G bond.
Weak nucleophiles. Do they react with carbonyls at all?
Notably, organomercury reagents generally do not react with simple ketones or aldehydes in a direct addition fashion. They're just not nucleophilic enough. However, Lewis acids can sometimes catalyze their reaction with reactive acyl chlorides to form ketones. With alkynyl mercury compounds, this reaction likely proceeds by electrophilic attack of the activated acyl chloride on the double bond, with the regiochemistry directed by stabilization of the intermediate carbocation by the mercury atom.
So if they're such weak nucleophiles and don't react easily with carbonyls, what are they used for in synthesis?
That's the key point. Most of the important synthetic applications of organomercury compounds involve their use in conjunction with transition metals.
Ah, partnership again, like with palladium coupling reactions.
Exactly. In processes like the Heck reaction or still-type couplings, though less common now than tin or boron, the organic substituent is transferred from mercury to the transition metal catalyst, often palladium, during the catalytic cycle. The palladium then does the main work of forming the new carbon-carbon or carbon heteroatom bond. So organomercury compounds serve as stable, handleable precursors that deliver the organic group to the active catalyst. They're strong partners, even if they aren't strong nucleophiles themselves. But again, like cadmium, toxicity concerns limit their widespread use today compared to less toxic alternatives like organoboranes or organosolanes. Okay, let's shift gears slightly to group IIb, indium. It's a congener of aluminum, below gallium. It has garnered significant interest in recent years for some unique synthetic applications.
Indium, what makes it stand out? Does it have a special trick up its sleeve?
It does have some unique properties. One is that its first oxidation potential is quite low, lower than zinc, and even lower than magnesium. This makes indium metal quite reactive as an electron donor, especially towards organic halides.
So it reacts easily with halides, like magnesium does.
Yes, but often with different outcomes or under different conditions.
Yeah.
For example, indium metal reacts readily with allylic halides, like allyl bromide, in the presence of aldehydes or ketones, to yield the corresponding homoallylic alcohols.
An allylation reaction, similar to the Barbier reaction we discussed.
Very similar in concept, generating the organometallic in situ and trapping it immediately. It's believed that this reaction involves an organoindium species, possibly formed via an intermediate indium species, and proceeds through a cyclic transition state.
Okay, allylation. What's the really special trick about indium, though?
The truly striking feature of many reactions involving indium metal and allylic halides is that they can often be carried out in aqueous solution.
In water, really, for an organometallic reaction.
Yes. It's quite remarkable and highly unusual for organometallic chemistry, which is typically extremely sensitive to water and periodic solvents. With indium-mediated allylations, the aldehyde or ketone acts as an efficient trap for the organoindium intermediate as it forms in situ, allowing it to react faster than it gets destroyed by the water.
That's amazing. Why is that so significant?
Well, it makes the reactions much more convenient, potentially safer, and environmentally friendlier, greener, than reactions requiring strictly anhydrous organic solvents. This aqueous indium-mediated allylation has been found to be widely applicable to various functionalized allylic halides and a wide range of aldehydes and ketones. It's a really neat niche for indium. Finally, let's touch upon the organolanthanide reagents. The lanthanides are that block of elements at the bottom of the periodic table, technically part of group IE-B, along with scandium and yttrium.
Lanthanides, like cerium, samarium. What's special about them?
Their chemistry is dominated by the +3 oxidation state, which is typically the most stable. These Lane3 ions are known as strong, hard Lewis acids, and they are particularly oxyphilic, meaning they have a very strong affinity for oxygen atoms.
Superoxygen lovers, right. How does that translate into synthetic utility in organometallic chemistry?
Because they love oxygen, They can coordinate strongly to carbonyl groups and act as Lewis acid catalysts to promote additions by various nucleophiles. In the context of organolanthanide regions themselves, organocerium compounds have seen the most significant development in recent years.
Organocerium, CL3 is common, right? How are they made?
They're typically prepared by reacting organolithium compounds, RLI, or sometimes Grignard regions, RMGX, with anhydrous cerium chloride, CCl3. The exact details of the ClO3 preparation, making sure it's truly anhydrous, and how it's reacted with the organolithium can actually be critical to the success of subsequent reactions. It's sometimes called the Imamoto reaction.
So you make RC-ClO2 or maybe R3CCs. What's the key advantage of using these cerium reagents instead of just the original lithium or Grignard reagent?
The main advantage is that these organocerium regions are particularly useful for carbonyl additions that are problematic with Li or MJ regions, especially cases prone to enolization, that unwanted alpha deprotonation, or additions to sterically hindered carbonyls.
Why do they help with enolization?
Organocerium regions seem to strike a good balance. They maintain strong nucleophilicity, so they still add efficiently to the carbonyl group. But they show a much reduced tendency to act as bases and cause deprotonation compared to their highly basic organolithium precursors.
More nucleophilic, less basic. That's a useful combination.
It really is. For example, in the addition of the bulky trimethylsilithium reagent to 2-indinone, a ketone with relatively acidic alpha protons, the yield was a miserable 6% using just the lithium reagent due to extensive enolization. But when the lithium reagent was first converted to the organocerium reagent using CL3, the yield of the desired addition product jumped dramatically to 83%.
Wow, that's a massive improvement, just by swapping Li for C.
Exactly. Organocerium reagents have been found to significantly improve yields in additions to other challenging systems too, like hindered bicyclic ketones or additions to the very sterically hindered 17-position carbonyl group on steroids.
So they're mainly for solving problems with difficult substrates.
That's a major use. But interestingly, even additions of standard well-behaved Grignard and organolithium reagents can sometimes be effectively catalyzed by adding just catalytic amounts, say 5-10 mol% of CCl3. The cerium likely acts as a superior Lewis acid activator for the carbonyl group in these cases.
Catalytic CCl3. Interesting. Do cerium reagents work well for making ketones, like from carboxylates?
Yes, cerium reagents derived from organolithiums have also been shown to give improved yields compared to using the lithium reagents directly in the reaction with carboxylate salts to produce ketones, that reaction we discussed earlier.
Yeah.
They also provide good yields of ketones when reacted with amides, especially those derived from piperidine and morpholine.
Why morpholine amides?
It's been suggested that the extra oxygen atom of the morpholine ring might coordinate to the oxyphilic cerium ion in the reaction intermediate, helping to stabilize the addition intermediate and prevent over-addition, similar to the Weinreb-amide mechanism. This procedure has been successfully used to prepare certain long-chain ketones needed as precursors to insect pheromones.
Very practical. Do they react with other things beside the carbonyls?
Yes, organocerium reagents also exhibit excellent reactivity toward nitriles and H-amines. Furthermore, organocerium compounds were identified as the preferred organometallic reagent for certain additions to hydrozones in an enantioselective synthesis of aminogens, again showcasing their potential for precision in asymmetric synthesis. Hashtag tag outro.
Wow. We have really journeyed through an incredible landscape today, covering the organometallic compounds of group 1 and 2 metals, from the absolute foundational Grignard and organolithium reagents,
The pillars of CC bond formation.
to the more specialized, nuanced applications of zinc, cadmium, mercury, indium, and the lanthanides like cerium. It's truly amazing how subtle differences in the metal's properties and the reaction conditions open up entirely new avenues, new possibilities for chemical synthesis.
It really is. What stands out most to me, I think, is that delicate balance we kept seeing between raw reactivity and fine-tuned selectivity. With Grignards and organolithiums, we get this incredible, almost brute force nucleophilic power.
Yeah, sometimes too much power, leading to side reactions like reduction or enolization or incompatibility with certain functional groups.
Exactly. But then you see how the less electropositive metals, like zinc especially, or cerium, leverage catalysts, Lewis acids, sophisticated chiral ligands to achieve highly controlled, highly selective, and even highly enantioselective reactions. They give us these incredibly precise tools for building complex molecules with very specific architectures.
It really highlights how chemists aren't just mixing ingredients together and hoping for the best. They're designing molecular dance partners, choreographing their movements, influencing how they interact, and precisely controlling exactly where new bonds form.
Molecular architecture by design.
Exactly. So what does all this complex chemistry mean for you, the listener? Well, it means that every time you encounter a complex molecule, whether it's a pharmaceutical saving lives, a natural product with amazing properties, or an advanced material with new functions, there's a very good chance that one of these incredibly versatile, sometimes finicky, but ultimately powerful organometallic reagents played a absolutely critical role in its creation. It's a hidden world of complexity, but also profound elegance.
Mhm. The sheer ingenuity that chemists have shown in developing methods to precisely control these often very reactive species, figuring out how to manage aggregation, how to direct lithiation, how to design chiral catalysts that give almost perfect enantioselectivity. It's just a testament to the ongoing quest for efficiency, specificity, and artistry in chemical synthesis. And maybe this raises an important question for you to ponder.
Ooh, leave us with something to think about.
Yeah. Given all the specific strengths and weaknesses we discussed today for each type of organometallic reagent, the power of lithium, the precision of zinc, the aqueous advantage of indium, the selectivity of cerium, how might a synthetic chemist actually decide which one is the right tool for the job when faced with a particular molecular transformation they want to achieve? What factors go into that critical decision?
Choosing the right tool for the molecular task. Definitely food for thought. Thank you for joining us on this deep dive into the truly fascinating world of organometallic compounds. We really hope you feel much more informed, maybe a little bit amazed, and definitely intrigued by the subtle magic of chemistry. Until next time, keep exploring, keep questioning, and keep learning.